Hello everyone. We continue with the window fiber amplifier. The amplifier gain can be obtained using a output power by input pump power. So we should know that what is the input pump power at a signal power there. So then wavelength of this pump and a signal wavelength there. So this output power depends upon the ratio of lambda p by lambda s. Now the signal output, or you can say that output power for this iridium low fiber amplifier, it is depending upon that pump power. So output is not exceed the pump power output for this iridium low fiber amplifier. If the input signal is very large, so for this given equation, that is for the gain, then the maximum amplifier gain is unity, and to achieve the maximum specific gain, so input signal power cannot exceed a given particular threshold value. We can obtain the maximum gain for this iridium low fiber amplifier by the ratio of PS out by PSA. So there are the various structures of iridium low amplifier, and it has a various configurations. So how we can use iridium low fiber amplifier? So in which three configurations. Here a co-directional pumping, then we have a counter-directional pumping, then a dual pumping. These are the three types or a configuration used in an optical amplifier. You see here that is signal, a tap, then isolator, then a pump source, a pumping laser, and through this your signal is propagating, that is EDFA, then optical isolator, then a signal out. So EDFA, we are getting the signal out, that is the pump is before that EDFA, and here EDFA, then pump, and then we are getting the output there. So you can have a co-directional pumping and a counter-directional pumping. Now in this case, a dual pumping is used to get the amplification. There are about the three configuration we are using. So for this EDFA, wavelength is used, that is selected by this wavelength selective coupler, and a signal that has a different wavelength. So selected wavelength for the pumping is to be considered, and then we are getting the output there. So now in EDFA, that is a spontaneous emission takes place. So we have seen in the receiver, optical receiver, that noise is depending upon the factor of short noise, thermal noise, and dark current noise. So we should know the noise figure of the receiver. Similarly, for the noise figure, total noise figure for this particular system, using the amplifier, we can obtain. So total noise figure for a given circuit we can obtain through this amplification. Here the wavelength, operating wavelength of EDFA, and for the given signal, noise slice. Here these are the noise slice, and this noise occurs because the signal generated at the given noise, and it has a noise signal interference in the given wavelength. So noise can be removed by narrowband filter, Or we can consider that amplifier signal noise for EDFA twice of NSP G minus 1 by G is equal to twice of NSP. It is depending upon that what is the signal, pumping signal we have. So we can consider this optical amplifier if we increase the use in a wide band. So we can use the number of optical amplifier in a series in a EDFA. So if we are using in a wideband application, so then each stages has a noise, so that is added in amplifier noise. So system performance evaluated using this EDFA depending upon that optical signal noise ratio, and it is defined as the ratio of a EDFA optical signal power output power to the unpolarized optical noise power. You can consider that the noise in the amplifier. So next we'll see the Raman amplifier. In the Raman amplifier, a concept of a scattering is used, Raman scattering. So Raman scattering is occurred in a fiber when we are using a high power, or we say that a optical signal propagates through the fiber if its level is higher than the threshold level, then scattering occurs. So generally, Raman optical amplifier is based on a nonlinear effect, and that is called as a stimulated Raman scattering, which occurs in the fiber at high optical power. This stimulated Raman scattering effect is occur due to the interaction between an optical energy field and the vibrational mode of the lattice structure in a material. So this scattering occurring in the given fiber when an intense pump beam propagates through it. So in this scattering, the incident pump photon gives its energy to create another photon of reduced energy at a lower frequency. The remaining energy is absorbed in the given medium in the form of molecular vibration, that is called as the optical photon. The frequency difference occurs, and that is called as a Stokes shift. And this shift is to a particular longer wavelength. So that's why it is called as the Stokes shift. And power transfer to the higher wavelength occurs over a broad spectral range of 80 to 100 nanometer. The energy difference between the absorbed and released photon is transferred into a photon which is a vibrational mode of the material. So in this Raman amplifier, if you see that we use a various nature of a glass, and that is used for the vibrational energy levels of the given silica, and that is the phenomena of a Raman scattering, so that it can be used for the different level of this wavelength, for the different wavelength. So then if you see the Raman scattering here, and the shift in the wavelength occur, so that resulting in the Raman gain, and we can consider here a Raman pump at 1445, and then if shift occur in this 90 nanometer, that is up to, you can say generally it starts from the 10 to 100 nanometer. So peak occur of shifting of 90 nanometer, and then signals at this 1535. So because of that, SR is generated interference signal at 1535. This one is a data signal, and we achieve the gain. The gain curve is given in terms of the Raman gain coefficient of a given amplifier. So we can have a different process to convert this, or we can use this Raman amplifier for this amplification. A typical example of a Raman amplification: hey, the input power, the power tab which monitor what is the output here, then total link, transmission fiber. This one is about your pump. It has the various wavelength. That various wavelength is used for the shift in the wavelength. This one is a coupler, that is pump power coupler. In GFF we can have filter for this, so we will get the output here. So this one is a typical diagram of a Raman amplifier, and that Raman amplifier is used for the amplification purpose. And this filter, it is depending upon what is the different input pump we are using. So for this particular power, so that's why the gain filter, gain flattening filter is used to equalize the gains at the different wavelength. And the pump source, it combines the multiplexes output at the output. So it operates at the different wavelength. And this combined pump power, and that is coupled to the transmission fiber. So that direction is about a counter propagating direction through the WDM, broadband WDM coupler. The difference in the power level measured between the two monitoring photodiodes, that gives us the amplification. So these are about the monitoring diode at input side and monitoring photodiode at the output side. So difference in this, we can obtain the what is the amplifier gain of a given system. So this one is about a Raman amplification, that is setup of a Raman amplification. So then there are the parameters of a Raman amplification for a 14xx nanometer pump. There are the different parameters and their performance values of a given particular parameter. Then a performance parameter of a broadband WDM used in this setup. So that is for the WDM. These are about the parameter, their performance values. Micro optics, if we consider the thin filter, then it has the parameter for this given particular amplifier. These are about the Raman amplifier. We'll see the difference of all these three amplifiers.